on, we're looking at question 1 of winter 2018 paper 4-1-9702. The first part reads, state what is meant by gravitational potential at a point. Now this is one of the many definitions from this chapter that is extremely important and something that should be in your mind all the time. That is, gravitational potential at a point is the work done per unit mass in bringing a small test mass from infinity to the point. In simple words, if I were to explain this visually, if for example I have my planet here and then I need, and this is, let's assume this is my infinity, and there is this any small mass. So this is extremely important, a small test mass, and it's per unit mass. So the energy that is required to bring this mass from infinity all the way till here, all the way to Earth, is the energy that's required. That is gravitational potential. That's it. Moving on towards our second part, that says suggest why for small changes in height near the Earth's surface gravitational potential is approximately constant. Now there is an entire relationship that we're going to be looking at in order to answer this question. Before that, we need to derive a formula or derive a relationship between height and the gravitational potential. How do we do that? We know that gravitational force is equals to gmm over r square, because that's gravitational, that's Newton's law of gravitation, that the force of attraction is directly between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of their separation. And in order to remove that proportion sign, we put a constant, which is the gravitational constant here. We have this formula right here. I'm going to be showing you here. And another force that we have is F equals mg. Which we have done in like in a lot of chapters, that W is equals to mg, and that W is force here. Now if I were to replace this F with this, I can get mg equals gmm over r square. Now you can see I can cut m here, and I'm left with g equals gm over r square. Now you do know that this g and m, they will remain constant, so we're only left with g and r square. So if I were to make a relationship, I can say that g is inversely proportional to 1 over r square. Now they say why for small changes in height near the Earth's surface gravitational potential is approximately constant. We will say that if you have small changes in height, let's assume this is Earth and this here is my radius, and I'm talking about this small height. Now this small height is way less than the radius, so I can say for changes that are very lesser, like the distance in simple words, I can say that for an insignificant distance compared to the radius, this insignificant distance compared to the radius, it remains constant. Why? Because gravitational potential is inversely proportional to the radius. So if this remains relatively constant, I can say g remains relatively constant as well. So we will say for an insignificant distance, or insignificant height compared to the radius, their gravitational potential remains relatively constant. Furthermore, you can add that since G is inversely proportional to the radius, and radius remains constant, so G is also approximately constant. And I hope this makes sense. Moving on towards the B part, that says the moon may be considered to be a uniform sphere with a diameter 3.5 into 10 raised to the power 3 kilometer and a mass of 7.4 into 10 raised to the power 22 kilograms. A meteor strikes the moon, and during the collision, a rock is sent off from the surface of the moon with an initial speed v. Assuming that the moon is isolated in space, determine the minimum speed of the rock such that it does not return to the moon's surface. Now, this question is pretty simple if we know which formula to use, but this often confuses students as to which formula we have to use to find v, because there are two formulas that contain this v. Number one is if you have gravitational force providing the centripetal force. For that, if the gravitational force is providing the centripetal force, then what we say is we have our gravitational force, that is gmm over r square, and we have our centripetal force as mv squared upon r. This m cuts out, one of the r cuts out from here, and we're left with gm over r as our v. This is one formula. Another formula is when we have to find the energies, and we say that at the surface it's sent off from the surface, and at the surface the kinetic energy, because both of them are initially equal, and gradually as the rock moves away from the earth, we can say the gravitational potential increases, or its kinetic energy it increases because it's now moving. But at the surface, when it's not moving, the kinetic energy is equal to the gravitational potential energy, and that we will write as 1 by 2 mv squared over equals gmm over r. Gmm over r. Again, I can cut this out and I'll be left with 2gm over r, and I can just take its under root and I'll get v. Now, this is our second formula. When do we know which formula to use? If the question says that this meteor was in a circular motion around the moon, if the word circular motion comes in the question, you're supposed to use this formula always. But if they say that it strikes the moon, it hit the moon, and there has been a collision, then you always use this formula. It's a set thing, and it's extremely important, because if you're not able to identify which formula to use, that can take these 3 marks away. Now that we know that we have to use this formula, that is 2gm over r under root, all you need to do is just plug in the values now. So we have v under root 2gm over r. Now if you plug in the values, you have g as 6.67 into 10 raised to the power minus 11. You have your mass as 7.4 into 10 raised to the power 22, and you have your r as 3.5 into 10 raised to the power 3 divided by 2, because this is the diameter, you have to divide this by 2. Once you plug in the values, you take the square root, you will get your answer for the minimum speed, and that is 2.4 into 10 raised to the power 3. 2.4 into 10 raised to the power 3. And this is it for question number 1.